In this video I want to introduce a little bit about the underlying data model of how mrTools stores the data and how things get created. So I'm back here in this session, currently in the folder. You can see on the right hand side here is a view of the files in the file system. And I'm going to open up a Mr. Loadred window, mrLoadred window here. And because we have this mrLastView file saved from before, it actually remembers some of the state of the GUI in the last session. So it moved it to the appropriate place, remembers which slice I was on, and has remembered some of the other settings of the buttons in the GUI. Now, to understand how some of the functions and analysis tools inside mrTools actually work, it's worthwhile knowing a little bit about how things are actually organized. Okay, so the data files are grouped together in groups. Okay, so when we start out with an analysis, we only have the data in the raw state. So there's a group called raw, and in this particular case, this contains 3 different files. If we look at the file system, this maps to raw time series data files that are in here, and I'll show you in a minute where some of that information, the metadata, is kept for this GUI to operate on this quickly. If we perform an analysis, like we'll do in a second, to transform the data, sometimes the result of that is a new set of images that need to get stored as Nifty files. Okay, and in this case, often a new group is going to be created. So let me just walk through this as a by way of example. So if I start out with a GUI and the data in the state that we left off in the last time, and I go to this analysis tab, and I'm going to perform motion compensation, which you could consider sort of an analysis step in a way, right? It takes some input data, performs some actions, some computations, and results in some output data. In this particular case, what we will get from the raw data is just a motion compensated version of the files that will get stored out. And there's various options here, but if we go with the full motion compensation first, this will pop up some options here. Again, there's some documentation if you're interested in all of the settings, but I'm just going to go through this here. So the first default setting here is the name of the group, the new group that will be created in which the results of resulting Nifty files and information will get stored. Okay, so we'll see that work in a minute. If we realign data by less than sort of 1 voxel, we need to think about how we interpolate. Linear interpolation is very quick and okay in most cases, but you have access to other options here too. So if you want to do spline interpolation, to be a bit more accurate, you can do that too. We need to decide which frame of the motion sequence we want to align everything to. So that's the stationary frame that everything is going to get referenced to. In this case, we have to decide which scan of the 3 scans that we have included in our data set is the base scan, the scan to which we want to align, and which of the images. And in this case, I'm going to align everything to the first time point in our first scan. So that's first in the base frame first. I will actually switch off slice time correction because I want this to go more quickly. In my personal experience, for short TRs, it may not even be worth the while doing this. There's some papers out there. Drift correction I'll leave on. I'm not going to do any temporal smoothing. And if I'm going to include all of the files by default, so there's an option here that allows you to exclude particular scans. So if you want to exclude one of the fMRI scans, then you could do that at this point here. Okay, so if I press OK, I actually paused the video while this was going on, but it's relatively quick, so it takes about a minute per scan here. you will see actually in the file system view here that under motion comp, which is a new folder that got created, the time series files are being saved out now here. Okay, so here's the first time series 4D data file that's been motion aligned. There's an additional mat file that contains information about the frame by frame matrices. Right, so the motion comp step is complete, and as you can see now there's 3 nifty files in this folder and 3 mat files to go along with it. I will go back to the GUI in a second, but I just also wanted to show you in the command window there's a couple of command line calls that you could use with mrTools to get information about scans and groups and so on. Okay, so if you use the command group info inside the folder, you will get sort of a pretty printed version of what groups are available. You can get help on group info as well. You'll see that if you give it the group number in this, or the group name, you will get some pretty printed information about the scans that are contained in that inside that group. Okay, so if I type just group info without anything, I get high-level information about which groups are available. If I type group info 1, I'll get information about the scans in group number 1. Equivalent would have been raw, right? It's the same thing. And it's very useful to be able to go back to finding out about the original data files. Maybe in your data sets you're mixing scans with different voxel sizes and TRs and dimensions and so on. It's very useful to be able to quickly look through those on the command prompt. If we now inspect the group number 2, which is the motion comp group that was created, you can see that the file names were auto created with some date stamps to make sure that we don't overwrite files with the same file name. And if we go back to the GUI window now, in the pull down option for groups, we can now select also the motion comp group. Okay, so if I go to this one here and switch back on the interrogator overlay function, we could just have a look at what the time course plots look like for this particular setting. So we go maybe here. You can now also see that for the motion comp group, because there's information about alignment matrices, some information about where voxels are in the scan space, the raw space and the magnet space are available. And we'll come back to alignments in a separate window at some point. Okay, just double check for the raw scans. Actually, they're also available. Just hadn't pointed them out before. All right. So what has happened is this whole set of files from the raw time series were converted into this motion comp time series. You can see where the information is actually stored on disk, but we now also have some metadata which gets stored in various data structures inside mrTools, which contains information that sort of is a bit ancillary to the actual raw imaging data. So what do I mean by that? So one thing, for example, that we could look at is how much motion compensation was actually done between frames. So that information is not stored in the images, but it's information that needs to get stored in some other data structures, right? So we need to have a 4x4 coordinate transform that tells the alignment program how to align each time frame of the scan to the base frame, and we can plot information about that. So for the motion comp group, we can now, for example, look at the motion correction matrices, get some additional plots here, and so this will show you for this particular scan the translation parameters and shear, and also an estimate of rotation as a function of which time frame of the 4D time series we try to align. Okay, so we're starting out here at 0. If I go to window and say I want a new graph window, which will allow us to keep this first one present, I now go to scan number 2 and I do the same plot. I'll get the plot, but not for scan number 1, which was this guy up here, but for scan number 2. Okay, and in this particular case, actually, the translation started not at 0 because the alignments are, so this is where the brain was located at the beginning of the second scan. So we start out at 0, 0, 0 in terms of translation for the first frame because that's where we aligned everything to. By the end of the first scan, everything has drifted away slightly from that, and that drift continues from roughly the same point in the second scan. Okay, so that's a useful thing here. Right, so the results of this analysis were actually a bunch of 4D data files, which we can't visualize as statistical maps, but there's this additional data which we can show as line plots. Let me show you another kind of analysis in which we are going to do some dimensionality reduction in the sense that we're going to calculate some statistic from the 4D images that results in 3D images of statistical maps. Okay, and as a starting point this time, I won't use the raw scans, but I will use the motion compensated scans, which are actually a much better picture of or cleaned up version of the data. So rather than going back all the way to the start with the untreated data, I want to now use the slightly improved data set for which we have removed some of the motion in the original data set. So with this tab set to motion comp, I will now go and perform some time series statistics, okay, which pops up a bunch of GUI windows. So the first thing that you see here, which is something that happens that you can make use of for your own analysis as well, is do you want to perform this analysis to only one scan or maybe all of them, right? In this case, by default, all scans are selected, and it tells me what the starting point is. In this case, I'm not starting with the raw scans, but the full motion compensated versions of the raw scans, which is the right thing. If you started with a tab at raw, you would have populated this GUI window with the raw data files instead. Okay, press OK, and you can see behind the scenes there's some time series statistics that have been calculated, right? So that's very quick because it just calculates mean, standard error, mean absolute deviation, and that kind of stuff. And now the result of these calculations is kept together in an analysis. Okay, so where does that actually show up? In the motion comp folder, which contains information about this particular group, we now have a separate subfolder, which is called time series stats, which is the person who implemented this particular statistical analysis decided that that was going to be the name of the results folder. So a similar thing would apply if you were doing a correlation analysis or something else. You'd get another subfolder. And in this particular case, all the additional information is stored only in a mat file. Okay, so the results of this analysis are stored here as an analysis, and it comes along with a whole bunch of overlays. Overlays are statistical parametric maps, so where you can display one scalar value usually for every voxel location in your data set. And there's a whole bunch of them here. So the first one that was calculated was actually the mean. So if we look at this, you now see this false color map of this mean image intensity over time. Okay, so the 4-dimensional data set was collapsed over time. At each voxel, where we have a time series, we took the mean across time, and the resulting number is stored at that particular location. There's a color map associated with this, which we can change if you don't like this particular color scheme. But I want to introduce some of the GUI buttons down here that will show you how you can make use of them to visualize different things. Okay, so by default, the whole statistical map is being shown, okay, in this color map. But let's say that I am not interested in showing the low intensity values, anything below 100 units of image intensity. So what I could do is I could just only display values that are between 100 and the maximum value. So if I set this minimum value for display to 100, it will start cutting out some of the voxels with lower numbers. Okay, we can maybe go up a little bit higher. Okay, and equally, maybe I'm not interested in seeing the really, really high intensities, right? So you can see here when you hover over the voxels down here in this region of the GUI, you can get some information about the value. So when I hover the mouse over here, oops, actually trigger the interrogator, which is not what I wanted to do. But I need to have it on to actually get the information. So the intensity here is 2074 on average. Here was 2098 and so on, so you can get some information here. So I imagine if I cut off about 2000, above 2000, then it will nix out the voxels at this particular location here. So one nice thing you can do if you're trying to find out the correspondence between certain results from a statistical analysis, say, and the underlying anatomy, is you can actually change the transparency. So if I change this to 25, you will see that the statistical map has become transparent. Maybe 0.5 to make it a bit more obvious. And so you get a bled out version of your statistical maps, which might be useful under certain situations. All right, so this is already quite useful. There's various options and for modifying this behavior, and this will allow me to introduce you to some of the options here. So for example, in the edit window, under the overlay tab, we can manipulate these overlays, get some information. So maybe let's get some information first. We'll give you some information about the alpha value that we set in the GUI here, what the clip values were, what the color map, how the color map is treated when it was created, what the tool was that created it, and so on and so forth. You can even export some of the overlay data for a quick look in your MATLAB script if you just want to bring it into the workspace. So that's quite useful. I will show you that in a later video. One thing we might want to do is, if I go to overlay here and say edit overlay, one thing you commonly want to do is change, say, the color map. Okay, so by default, the color map is whatever the person who implemented the analysis is. In this case, it's jet, but that might not be a good way of showing increases in intensity. So maybe hot might be a better map. It's easier to interpret. And this is one way in which you can modify the behavior here. Okay, so let's say at this point already you might want to keep a screenshot. You can actually do that right here. So you can say print, which won't do the print window. It will produce a separate figure window in MATLAB that you can then use to export into one of the various formats. So that's sort of a useful intermediate point for doing some of these analysis. All right. The next step is to manipulate some of the data and some of these intermediate results we got by actually looking at them from a scripting point of view, maybe from inside a function. And in order to illustrate that, what I will do is I will introduce this idea of how we can access data that's stored in this combination of files on disk and metadata inside various data structures And this brings me to this idea of views of the data. And in the next segment of this video, I will explain this a little bit more.